Welcome to part 2 of the 8.2 class notes. So I know that you might think this is the next place we're going to take class notes, but there's a couple of things that we wanted to add or adjust in these places above that class notes section. And the first one is polyatomic ion. The definition from the book is fair. It is a tightly bound group of atoms that have a positive or negative charge and behave as a unit. But if you look at this, if you break this word down, poly means many and atomic is atoms, and then ion means has a charge, right? So really, if you wanted to add a simpler definition to this box, you could say it is a group of atoms with a charge. A group of atoms with a charge. Now this next box is that compounds containing polyatomic ions include both, and this was a literal sentence from your book, so include both ionic and covalent bonding is what you should have written in there. Include both ionic and covalent bonding. But I want to just explain this a little bit further, okay? So I'm gonna add to that. So hopefully you have ionic and covalent bonding written here. We're gonna add to that, okay? The atoms are covalently bonded . The atoms are covalently bonded, and remember, covalent means sharing electrons. So all of the atoms within the ion are covalently bonded, okay? But it is an ion. It is an ion. That whole unit is an ion, and will have ionic bonds in the compound. And will have ionic bonds in the compound. Okay, so the atoms are covalently bonded, but it is an ion and will have ionic bonds in the compound. That's what we've got there, okay? All right, so as an example, we're going to draw a polyatomic ion. We're going to draw NH4 with a positive charge. So NH4 plus, it's not a 4 plus charge, it's 4 hydrogens and a positive 1 charge. This is called ammonium. Well, we're going to follow the same 3 steps that we were following earlier when we were just drawing molecules, okay? Because this is basically a molecule that has a charge. So my neediest goes in the middle, and if I look at my periodic table, I've got nitrogen right here, needs 3 more electrons to be stable. Hydrogen, remember, only needs 1 because it's going for the same configuration as helium. So nitrogen is my neediest. The 4 hydrogens go around the outside. There I have my neediest in the middle. Second step, distribute the electrons. Give each atom 8 valence electrons except hydrogen. So I'm just going to give 8 to nitrogen, which would make it stable. That also makes each hydrogen stable because now they have 2, and that is the same configuration as helium. Okay. All right, add, count, compare. So nitrogen, when we look at that periodic table one more time here, nitrogen has 5 valence electrons because it's part of group 5A. Each hydrogen only has 1 valence electron because it's part of group 1A. Okay, so 5 plus 1 from each hydrogen, and there's 4 hydrogens, so 4 equals 9, okay? Now, wait a second, the picture only has 8. We are not done. We're not done adding, okay? The reason we're not done adding is that positive charge right there means what? Hopefully you remember from our previous chapter that when something is positive, it has lost electrons. When it's positive 1, it has lost 1 electron. So this entire structure has lost an electron. So I get to subtract 1 from this total, and that equals 8. Okay? So we're still working with even numbers of electrons so far. Okay, so 8 is the number of dots I should have, and then 2, 4, 6, 8. I do have that many. Now with polyatomic ions, there's one more step. You always have to put the entire structure in brackets. Brackets are square, not parentheses, okay? Make sure that you're getting that right. That's the same with our abbreviated electron configurations. We need to see brackets, not parentheses, around those noble gas symbols, okay? But brackets around the polyatomic ion structure, and then we put that charge on the outside. So this is telling me why this structure has 8 instead of 9 electrons, because we've lost one and it's got a positive charge, okay? All right, down at the bottom, we've got exceptions, and exceptions are always a nice place to get extra credit, okay? So first of all, our odd number of electrons, okay? If you already have something written, you can maybe write down below whatever you need to do, but I want you to go ahead and write nitrogen can be stable. Nitrogen can be stable with 7 valence electrons. Nitrogen can be stable with 7 valence electrons, okay? I'm going to use NO2 as an example to show you this. So nitrogen would be in the middle, it's the neediest. Go ahead and put everybody around, give everybody 8. Okay, that's our start. Nitrogen, when we look at the periodic table, has 5 valence electrons. Each oxygen, when you look at the periodic table, has 6 valence electrons, so 6 times 2 is 12. So altogether, my structure is only allowed to have 17. Now there's no charge, so I'm not going to be adding or subtracting from that 17, but altogether I'm allowed to have 17. Well, if I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, way too many. So we have to do an erase a pair, add a pair to share. Now remember, when we're erasing, we have to erase from 2 atoms that are attached to each other, because if I erase from each of these oxygens, where am I going to put the pair to share so that everybody still has 8? Can't do it. So I'm going to erase a pair from one of the oxygens and one of the pairs from nitrogen. Okay, now if I left it like that, these 2 wouldn't be stable. They only have 6. So I add that pair to share in between them, so that they still each have 8. If I were to cover one up, you still see 2, 4, 6, 8. Okay, covering up the oxygens here, you still have 2, 4, 6, 8 around nitrogen. Okay, but count again, 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, I have to get down to 17, and this is where, if we remember this rule, nitrogen can be stable with 7, then we just erase one of the electrons. Going to erase both and redraw one, okay? We erase 1 from nitrogen, and now it has 7. Total is reduced down to 17, and that's my structure. So that's one of the possibilities that you might see for extra credit. Another exception to the octet rule here is going to be boron. Boron is just B. Boron is always stable . Boron is always stable with 6 valence electrons. With 6 valence electrons. Okay, so I'm going to go ahead and draw BF3 as an example. Boron is going to be the neediest. If you look here, it only has 3 valence electrons, so it's really not close to having an octet. Fluorine has 7, so it only needs 1 more. So boron is my neediest here, so it goes in the middle. And then I surround it with 3 fluorines. Give everybody 8 like it tells me to in step 2 up above. I don't have any hydrogen to worry about as far as an exception goes. And then we add, count, and compare. Well, boron, if we look again, boron is in group 3A, so it has 3 valence electrons. Each fluorine has 7, so that's 21 total from the 3 fluorines. So this equals 24. Okay. Now if I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I have too many. Normally, we would go to this erase a pair, add a pair to share step, and we would make a double bond between boron and one of the fluorines. Okay. But we just need to try and remember boron is always stable with 6 valence electrons. So I'm going to erase that pair right there, and this is my actual structure. So boron is totally weird, different from any other element we've looked at so far, and here's why. It only has 5 protons. So attracting 5 more electrons when your total positive charge is only 5 to begin with, and it already has 5 electrons to use up some of that attraction, That's not very likely, and it doesn't happen in nature. Likewise, losing 3 electrons to get down to the same number as helium would be really difficult because that's over half of the electrons in a boron atom. So that's why this happens, but just remember it and you can get some extra credit. All right, finally we have more than 8 valence electrons. Now this is something that commonly happens with elements of phosphorus and sulfur, okay? Phosphorus and sulfur can have more than 8 valence electrons. Phosphorus and sulfur can have more than 8 valence electrons. And just to let you know, phosphorus could have 10. Sulfur could have 12. Okay? So as an example, if I have a compound PCl5, and again, that's a chlorine, not a carbon with 5 iodines, okay? We will try to make it super obvious when it's an I. We'll cross the top and bottom of it, okay? But we've got PCl5. Well, phosphorus is the neediest because it needs 3 more to fill its valence shell. Chlorine only needs 1. But there's 5 chlorines. So if I really want phosphorus to be the central atom and not have a chlorine in the center as well, I have to kind of get out of my little 4-sided imagination of how this looks. Okay, so what I'm going to do is I'm going to go ahead and put a chlorine, or all 5 chlorines, around phosphorus like this. I'm using dashes. Remember, a dash can represent 2 dots. So what I've just done there is I've given phosphorus 2, 4, 6, 8, 10. Okay? If you want to do this with dots, you can. Just arrange those 5 chlorines around. Give all of the chlorines 8, and you'll have 10 dots around your phosphorus. Okay? But this is the start for me. I use dashes because it can get a little bit messy with all those dots. You can also use dashes when you're doing bonds in any of these structures. Okay? But we're going to go ahead and give everybody 8. Ignoring the fact that phosphorus already has 10, I'm just going to go back and give chlorines all 8 of their electrons. Okay, so just go back through and add 3 lone pairs to each chlorine. Now this is one place we do not want to see dashes. We don't want to see dashes for lone pairs. We want to see a pair of electrons. Okay, so you can use dashes instead of dots when you're making bonds, but don't do that for those lone pairs. Okay, phosphorus has 5 valence electrons, and each chlorine has 7. 7 times 5 is 35. Add those 2 together. I know I didn't line those up right, but this is 40. And if you were to count the dots in the picture, you'd have 40, remembering that each dash counts as 2 dots. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. There you go. All right. Moving over here, we have a little bit more before we're done with this section. Okay, so first of all, resonance structures. Resonance structures are what happen when there's more than one way to draw the correct structure for a molecule, okay, or for an ion sometimes. Okay, so we are going to look at what happens. But first of all, we have to talk about how they're represented. They're represented by drawing all structures, all of the possibilities, and placing double-headed arrows between them. Placing double-headed arrows between them. Placing double-headed arrows between them. And so that can look like this. A single arrow with 2 heads, or you can stack your arrows like that. You'll see it lots of different ways, okay? But if you have arrows pointing in both directions, that's what we're talking about, okay? Now, the real structure of the molecule, this is something that I didn't think was super clear in our textbook. So the real structure of the molecule is a combination of all the possible structures with all equal bonds. Okay, and now I'm going to show you an example here, and then I'm going to talk to you about what I mean by that. So here's the example for this one. We're going to go SO2. SO2. Okay, this is going to happen a lot with polyatomic ions, but I'm just going to use a neutral molecule in order to show it and make it a little bit less complicated. Okay, so SO2, well, we have sulfur, which needs to gain 2, and we have oxygen, which needs to gain 2. So in this example, the neediest is a little bit more complicated. It's not going to be the neediest, it's going to be the largest. As we go down a group, things get larger, so that one has more room to make multiple bonds. So that one's going to be in the middle, SO2, so 2 oxygens attached to a sulfur. Okay, second step, give everybody 8 except for hydrogen, but we don't have hydrogen. And again, if you want to do dashes instead of dots for the bonds, you can. Just make sure that you're using 1 dash to represent 2 dots. Okay? All right, now add, count, compare. Well, they both have 6, right? So 6 from the sulfur plus 12 from the 2 oxygens is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, so now I have my third step. Erase a pair, add a pair to share. Erase a pair, add a pair to share. Remember, you have to erase from 2 atoms that are attached to each other. Let me show you how you cannot do this. Do not erase this pair, and then erase this pair, and then add a pair back in. So when I add like this, okay, this oxygen is still stable, 2, 4, 6, 8, okay? But this one out here only has 6, and the sulfur in the middle has 10. You cannot do that, okay? We have to keep all atoms stable, so we have to erase pairs from atoms that are attached to each other. So if I erase from that right oxygen, I also have to erase from the sulfur and then add a pair between them so that the sulfur still has 2, 4, 6, 8, and both oxygens still have 2, 4, 6, 8, 2, 4, 6, 8. So everybody's still stable. I have a single bond on the left and a double bond on the right, but I could have done it the opposite way. I could have chosen to erase from this end of the molecule. In other words, I'll draw it one more time. Giving everybody 8 here. I could have erased from this oxygen and the sulfur, okay, since those 2 are they're attached to each other, and then added between those 2, which gives me a double bond on the left and a single bond on the right. Now, those are different because of where the double bond is. It's not about which pair I erased on the oxygen or which pair I erased on the sulfur. Don't think like that. There are only 2 ways to draw this molecule. One with the double bond on the right and one with the double bond on the left. It does not matter which pair of electrons I erased to make that double bond. As long as the double bond is here, it's the same molecule, okay? Now, in reality, this molecule does not have a double bond and a single bond. Double bonds are a lot shorter than single bonds. Single bonds are a lot longer. But if we look at this molecule in an electron microscope, the bonds are exactly equal in length, and they're somewhere in between a single and a double bond. So in reality, we draw this double arrow to represent that the real molecule is kind of a combination of these 2. It's somewhere in between. It is not bouncing back and forth between these 2, but it's actually a combination of those structures, okay? So that is how we do resonance. Go ahead and answer your lesson check questions, do your sample problems, and then you'll get a video to show you how these are done, and you can check your work. Thanks.